Why does time pass slower in your basement than it does in your attic? Most people believe time is a constant drumbeat. Tick-tock, tick-tock. The same for you, the same for a star, the same for the universe. You think a second is a second is a second. That belief isn't just a little wrong. It is fundamentally, catastrophically wrong. Here is the cold, hard reality. If you take two identical atomic clocks, synchronize them perfectly, and put one on the floor and lift the other just 1 foot higher, they will disagree. The clock on the floor literally runs slower. We have measured this. It's happening in your living room right now. Your feet are actually younger than your head. You have felt this. Think about that heavy, sluggish feeling you get after a long flight, or the weird distortion of time during a car crash. Your brain knows time is flexible, but your textbooks lied and told you it was rigid. Gravity doesn't just pull on matter, it pulls on time itself. It drags the future into the past. And once you understand the mechanism, the actual gears grinding underneath reality, it changes how you see space, time, matter, and energy forever. Let me show you. Look at your watch or your phone. Do it right now. Watch the seconds tick by. 1, 2, 3. What are you actually seeing? You're seeing a mechanism counting, a crystal vibrating, a gear turning. We built these machines to chop up our day into neat little slices so we don't miss our dentist appointments. We invented the second. The universe didn't. And because we invented it, we made a massive assumption. We assumed that the canvas of the universe, the background stage where everything happens, is flat and frozen. Picture a giant infinite sheet of graph paper. In this old way of thinking, called the Newtonian view, I could place a bowling ball here, a planet there, and a black hole over there. The graph paper doesn't care. The grid lines stay straight. The time coordinate is the same at the corner of the paper as it is in the center. Nice, tidy. Wrong. That graph paper, it's not paper, it's molasses. This is the part nobody tells you. Space isn't empty. It is a physical thing. It has properties. It can stretch. It can twist. It can vibrate. And most importantly, it can flow. Imagine you are a fish swimming in a river. If the water is calm, you swim at a steady speed. But what happens if you swim near a massive drain? The water starts rushing faster, right? To stay in the same spot, you have to swim harder. Gravity is that drain. Matter, like the earth under your feet, is constantly sucking space toward itself. It's inhaling the grid lines. Now here is the counterintuitive leap. If space is being sucked down, what happens to time? They aren't separate things. We call it spacetime for a reason. They are woven together like threads in a rug. You pull the red thread, space, the blue thread, time, bunched up with it. When you stand next to a massive object like Earth, you are standing in a region where space is literally falling past you. And because space and time are locked together, time gets stretched out. Think of it like an audio tape. If you play a tape at normal speed, the voice sounds normal. Hello, that's space flowing normally. Now imagine stretching that tape out physically while the playhead is running over it. The sound slows down. Hello. That is what gravity is doing to your watch. The Earth is heavy. It creates a deep dent in the fabric of the universe. In that dent, the tape of reality is being stretched. The deeper you go into the dent, meaning the closer you get to the ground, the more stretched the tape becomes. So, down on the floor, the tape is stretched tight. Time plays slow. Up on the ceiling, the tape is relaxed. Time plays fast. But here is where your intuition fails. You might say, okay, sure, maybe near a black hole, but Earth? Is it really enough to matter? We rely on this stretching every single day. If we didn't account for this time dilation, the GPS in your pocket would fail within 2 minutes. The The satellites are high up in weaker gravity, so their clocks run faster than the clocks in your car. If engineers didn't program them to artificially slow down, Google Maps would tell you you're in the middle of a cornfield when you're actually on the highway. The difference is real, it is measurable, and it is keeping you from getting lost. But why? Why does mass stretch the tape? What is the mechanism that links a rock to a clock? Hold that thought, because to answer that, we have to break the speed of light. So we have a problem. We know gravity stretches time. We know your feet are younger than your head, but we need to know how. The answer is hiding in the speed of light. You've heard the number, 299,792,458 meters per second. We usually treat this as a speed limit, the maximum velocity of the universe. That is a boring way to think about it. Don't think of it as a speed limit. Think of it as a conversion rate. It is the exchange rate between space and time. Here is the rule that breaks the universe. Light does not care about you. If you are standing still, light passes you at c. If you are in a rocket ship moving at 99% the speed of light, that beam still passes you at c. This shouldn't be possible. If I throw a baseball at you and you run away, the ball hits you softer. Velocities should subtract. But light? It refuses to change its speed. So if the speed of light is fixed, something else has to break. Speed equals distance over time. If the speed side of that equation is locked by the laws of physics, then distance and time must be flexible. They have to rub a band to keep the speed constant. Now watch what this implies. Imagine a photon, a particle of light, trying to escape from a massive star. Gravity is pulling on it. But remember, gravity isn't a force pulling the photon. Gravity is the star curving the road the photon is driving on. The star creates a valley in space. The photon has to climb out of that valley. Because the road is curved and stretched by the mass, the photon has to travel a longer distance to get out than if the space were flat. But wait, the photon cannot slow down. It has to travel at c, always. So you have a particle that must cover more distance due to the curve, but isn't allowed to change its speed. How does it arrive on time? It doesn't. From the perspective of someone outside the gravity well, looking in, that photon appears to be vibrating slower. Its frequency drops. It loses energy. We call this gravitational redshift. But from the perspective of the clock sitting next to the star, that clock must tick slower. Here's the part that melts your brain. You are always moving through space-time at the speed of light. Right now, sitting in your chair, you are moving through the time dimension at the speed of light. Think of your reality as a car driving on a flat salt flat. You can drive north, space, or you can drive east, time. But your car has one gas pedal, and it is bricked to the floor. You are always going maximum speed. If you drive purely east, sitting still in space, 100% of your speed is used for time. You age at maximum speed. But if gravity shows up, gravity grabs the steering wheel. Gravity turns your car. It forces you to divert some of your speed into the spatial dimensions, falling. If you turn the car north, you aren't pointing perfectly east anymore. You have borrowed some speed from time to move through space. The more gravity curves your path, the less velocity you have available for ticking seconds. So, near a massive object like a black hole, your car is turned almost entirely into space. Your motion through time slows to a crawl. You aren't just waiting slower, you are literally traveling through the temporal dimension at a reduced velocity. That sounds impossible until you see the trick. Gravity isn't just pulling you down. Gravity is rotating your future into space. It turns tomorrow into down. This idea that down and future are interchangeable, it didn't just appear in a textbook. It hit one man like a lightning bolt. The year is 1907, Bern, Switzerland. Albert Einstein is sitting in a patent office. He's not famous yet. He's just a guy reviewing blueprints for electric synchronized clocks. He's staring out the window, likely bored, looking at the rooftops of the city. He sees a workman on a roof. And then Einstein has what he later called the happiest thought of my life. He thinks, if that man falls off the roof, he will not feel his own weight. Stop. Think about that. If you jump out of a plane before the air resistance hits, you feel weightless. You feel like you are floating. If you took a pen out of your pocket and let go, it would float right next to you. Most people would say, well, yeah, because you're falling. Einstein said, wrong. He realized that falling is the natural state of motion. When you are falling, gravity has disappeared for you. But right now, sitting in your chair, you feel heavy. You feel your butt pressing into the seat. Why? Because the floor is rushing up to hit you. This is the pivot that changed history. Einstein realized that sitting still on Earth is physically identical to being inside a rocket ship deep in space that is accelerating upward at 9.8 meters per second squared. If you are in a rocket accelerating up, the floor smashes into your feet. You feel heavy. If you are on Earth, the floor smashes into your feet. You feel heavy. There is no experiment you can do to tell the difference. This is the equivalence principle. Now, hold on to your seat because here comes the twist. Imagine you are in that accelerating rocket ship. You drill a hole in the wall and shine a laser beam through it, horizontally. While the light is traveling across the room, the rocket ship moves up. So, where does the laser hit the opposite wall? It hits lower than where it started. To you, inside the ship, it looks like the light beam curved down. The floor rushed up to meet it. Okay, simple enough. But remember the equivalence principle? Gravity and acceleration are the same thing. If light bends in the rocket ship, light must bend on Earth. Einstein realized gravity must pull on light. But light has no mass. Newton said gravity only pulls on mass. So how can gravity pull on light? It can't. Unless gravity isn't pulling. Unless gravity is curving the room itself. If the light travels in a straight line, but the room is curved, the path looks bent. And if gravity curves space, it must curve time. You cannot have one without the other. This was the moment the clockwork universe shattered. Einstein realized that the man falling from the roof wasn't moving through a static background. He was sliding along the curved geometry of reality. He wasn't falling. The Earth was rushing up to catch him. This implies something terrifying about your own body. It means your head and your feet are in different accelerating frames. Your feet are being pushed up harder than your head is. The acceleration at your feet is slightly different than at your head because they are closer to the center of the Earth. This difference is microscopic for you, but for the universe, it is the engine that drives everything. So we have the mechanism, the speed of light conversion. We have the history, the falling man. But you shouldn't believe me yet, because talk is cheap. You need proof. I'm going to show you 3 specific cases, from your kitchen to the edge of the galaxy, where this effect isn't just theory, it's visible. You still don't believe me. You think, okay, Einstein had a happy thought about a falling guy, but does the universe really care about my feet? Yes, and I'm going to prove it to you in 3 ways. The first is a thought experiment you can do in your head. The second is a piece of technology you use every day. The third is a monster lurking in the dark. Imagine a clock, but not a normal clock with gears. This is the simplest clock possible. It's 2 mirrors, one on the floor and one on the ceiling. A single photon of light bounces up and down between them. Tick, tock, tick, tock. Simple. Now, put this clock on a rocket ship that is zooming past Earth at incredible speed. From inside the ship, the photon just goes up and down, straight line, normal time. But what do you see from Earth? As the ship moves sideways, the photon can't just go up and down. It has to travel diagonally to hit the moving mirrors. It traces out a zigzag path, like a saw blade. A diagonal line is longer than a straight vertical line. We know this. It's the hypotenuse of a triangle. So the photon has to travel a longer distance. But remember the rule? The speed of light cannot change. It cannot speed up to cover that extra distance. So what happens? It takes longer to complete one tick. To you, standing on Earth, the clock on the rocket ship is ticking in slow motion. The moving clock runs slow. Now replace speed with gravity. When you stand near a massive object like a planet, you are essentially accelerating against the curvature of space-time to stay still. The deeper you are in the gravity well, the more acceleration you need to resist falling. The math is identical. The photon in a strong gravitational field has to work harder to climb out. It loses energy, its frequency drops, its tick gets longer. This isn't just a drawing on a whiteboard. We built it. This is where it gets real. In 2010, researchers at NIST, National Institute of Standards and Technology, decided to stop messing around with rockets and black holes. They wanted to measure time dilation in a single room. They took two of the world's most precise atomic clocks. These aren't normal clocks. They use the vibrations of aluminum ions. They are so accurate they won't lose a second in 3.7 billion years. They put one clock on a table. They put the second clock on a step stool, just 33 centimeters higher, about 1 foot. They turned them on, and they waited. If Newton was right, the clocks would stay perfectly synchronized. If Einstein was right, the clock on the table, being slightly closer to the Earth's center, should feel stronger gravity. It should run slower. The result? The lower clock ran slower, precisely as predicted. They measured a difference in the flow of time across a distance of 1 foot. Let that sink in. Every time you stand up, your head is aging faster than your heart. Every time you tie your shoelaces, you are dipping your hands into a slower stream of time. It is imperceptible to your biological senses, but it is a fundamental fact of your existence. You are a time machine. Your body is spanning different ages. But 33 centimeters is small potatoes. Let's go to the extreme. What happens if you take this to the limit? If Earth slows time a little bit, what if we squeeze the Earth down? Same mass, smaller size. The gravity at the surface gets stronger. The dip in space-time gets deeper. Squeeze Earth into the size of a marble. Now you have a black hole. The slope of space-time becomes a cliff. If you were to watch a friend fall into a black hole, you would see something terrifying. As they get closer to the event horizon, the point of no return, the light coming from them has to climb out of an infinitely deep hole. It loses so much energy that it redshifts into invisibility. But before they fade, you see their time slow down. You see them wave at you, but the wave gets slower and slower. Eventually, right at the edge, time stops. To you, they never fall in. They just freeze there, fading into darkness, trapped in an eternal moment. Their image is plastered on the horizon forever. But for them, they fall right through. They look at their watch and it's ticking normally. They cross the horizon in a split second and rush toward the singularity. This is the ultimate disconnect. You see them stop forever. They feel themselves fall instantly. Two realities, both true. This shattered the idea of a universal now. There is no now that applies to everyone in the universe. Now is a local illusion. It depends entirely on where you are and how fast you are moving. Your now is unique to you. Think about what just happened. We started with a clock on a shelf. We ended at the edge of a black hole where time freezes. The mechanism is the same. It's just the volume knob turned up. But here is the question that should be bothering you. If time is slowing down, where does the lost time go? Is it destroyed? No. This is where we have to leave the physics of the 20th century behind and look at something much deeper. Something that suggests time isn't just a measurement. It's a dimension you can rotate. It's not just about clocks running slow. It's not just a party trick with aluminum ions. It's deeper. We have been talking about time as something that happens to you, like rain falling on your head. But what if time is actually something you are doing? Remember the car driving on the salt flat? Let me say that again. You are always moving through space-time at the speed of light, c. That is your velocity vector, always. When you are sitting still in space, your entire velocity is pointing in the time direction. You are racing into the future at 1 second per second. But gravity rotates your velocity vector. When you stand on Earth, the mass of the planet is literally tilting your future. It is taking some of your speed out of the time direction and pouring it into the space direction. But here is where your intuition fails completely. You think, wait, I'm not moving. I'm standing still on the ground. Wrong. You are moving. You are constantly accelerating upwards. The ground is pushing you up. If the ground disappeared, you would follow the natural path of space-time, falling. So standing still on Earth is equivalent to accelerating through space. And because you are accelerating, you are constantly rotating your velocity vector. You are constantly turning out of the time dimension. This is why time slows down. You are literally using up your speed to fight gravity. You are trading time for space. And the stronger the gravity, the more you have to trade. Near a black hole, you have to trade almost all of your time just to hold your position in space. If you could hover right at the event horizon, you would be using 99.999% of your speed limit just to stay put. You have almost nothing left for the future. This means time isn't flowing past you. You are flowing through time. And gravity is the friction that slows you down. Now zoom out. Look at the universe. It's full of stars, galaxies, black holes. Each one is a dimple in the fabric. Each one is a slow spot. If you could see time, if you could put on special glasses that showed you the flow of time, the universe would look like a turbulent ocean. Near every star, time would be viscous, thick, syrupy. In the empty voids between galaxies, time would be thin and fast, rushing by. The universe isn't aging at the same rate. A clock floating in deep space has ticked more time since the Big Bang than a clock on the surface of the sun. Think about that. The center of our galaxy is actually younger than the edges. Matter drags the past with it. It creates a drag on history. And this leads to the most terrifying realization of all. If time is flexible, if my now is different from your now, then the past, present, and future might all exist simultaneously. Think of a loaf of bread. You can slice it straight down. That's one moment in time. But if you tilt the knife, you get a different slice, a slice that includes part of the crust, past, and part of the middle, future. Gravity tilts the knife. Speed tilts the knife. By moving, or by standing near a planet, you are slicing the universe at a different angle. This implies the block universe, the idea that the future is already there, waiting for us to arrive. The past isn't gone, it's just over there, in the block. And gravity is the lens that distorts our view of the block. When we see a star's light bend around a massive galaxy, we call it gravitational lensing. We are seeing light take a curved path, but we are also seeing time take a curved path. We are seeing events happen out of order from our perspective. So when your GPS tells you to turn left in 500 feet, realize what is happening. The satellite sending that signal is less deep in the gravity well than you are. Its heart is beating faster than yours. Its atoms are vibrating quicker. It is aging faster. It has to artificially hold its breath, electronically pausing its own clock, just to synchronize with your slow, heavy existence down here on the surface. You are living in the slow lane. The gravity of Earth is literally holding you back from the future. It's a prison, but it's a comfortable one. Because without that gravity, without that curvature, without that slowing of time, The Earth wouldn't hold its atmosphere. The sun wouldn't burn. The universe would be a cold, dark, fast place where nothing ever had enough time to happen. Gravity slows time so that complexity can exist. It buys us the moments we need to be alive. So the next time you look at your watch, don't just see gears turning. Don't just see numbers changing on a screen. See the deep, invisible river you are swimming in. Feel the heaviness of the earth pulling on the fabric of reality, dragging the future into the present, slowing down the ticking of your own heart. Realize that your head is aging faster than your feet, that the astronauts on the ISS are aging faster than you, that the core of the Earth is actually years younger than the surface. Time isn't a metronome, it's a landscape. It has hills and valleys. It has fast lanes and slow lanes, and you are constantly navigating it, whether you feel it or not. You are a time traveler. We all are. We are just traveling into the future at slightly different speeds. Gravity is the engine of that difference. It is the curvature that makes the journey interesting. It keeps us grounded, yes, but it also bends the rules just enough to make the universe possible. So when you feel that heavy sensation in your legs after a long day, maybe it's not just fatigue. Maybe it's just the weight of time flowing a little slower down there near the floor. And if you ever feel like time is slipping away too fast, just remember, the closer you get to something massive, the more time you have. Go find something heavy and hold on tight.